Good evening. Today is the extra class for the doubt session of the course named Interfacial Fluid Mechanics. And I'm Anvesh, and today we'll be looking at hopefully two of the previous year assignment solutions. So I'll begin. So let's look at the week 10 assignment. So let me get the question. So in this particular week, you have been looking at the Bernard-Marangoni instability. So we have thermal effects and Marangoni stresses. So let's look at the first question. Okay. So let us consider the stability analysis of a thin film, like a soap film or a tear film on the eye. Assume that the interface of the thin film is initially covered with a uniform layer of insoluble surfactants, tiny molecules which reduce the surface tension. Next, neglect gravity and van der Waals forces. Can you set up the problem of stability analysis of such a film using normal mode analysis? In which way do you think surfactants will affect the stability of a thin film to small perturbations? So the options we have is surfactants will play no role in the stability of the thin film. Surfactants generate Marangoni stresses which will destabilize the thin film. Surfactants generate Marangoni stresses which stabilize the thin film. So let's first write down what is given. So given we have no gravity. Gravity is zero, and Hamilton constant is zero. That is um, the forces forces are zero, and we have uh, we have to find. So we are looking for the effect of surfactants. So let's say our surfactants is a function of position vector, which is gamma naught plus 1 minus beta capital gamma of x minus capital gamma naught. So this is how the surface tension is varying due to the um, uh, let's say it's varying like this in space. It's a simple model, but let's look at the graph that we have for stability between Marangoni number Ma and alpha. And the Marangoni number can be written as rho naught, gamma naught, delta T, delta T by mu naught square. So what is of importance for us here is this gamma naught term. And we know that the curve for a constant Nusselt number looks like this. So Nusselt is equals to constant, and the curve basically divides the area into unstable and stable regions. So let's say we start at a point here, and we start at a point here and reduce the surface tension. As we reduce the surface tension, our stability increases. So, so therefore, the one of the um, one of the effects that surfactants have is that they reduce the surface tension. So therefore, the correct answer here is answer C. So as the surface tension gamma naught reduces, the the stability increases. So therefore, we can say that the surfactants reduce gamma naught. So therefore, we can overall say that the introduction of surfactants increases the stability. We can also see this through an example. So let's say another example is that you have a soap bubble and you have a normal bubble. In real life, you must have noticed that the soap bubble is more stable. So this is the bubble that you have uh, a soapy fluid, and then you blow out bubbles, and then you may have noticed that they have a longer uh, life, as in they stay in the shape for a longer period. Whereas if you try to create a normal bubble with higher surface tension, it tends to break away as soon as it's formed. So this is also an example to show that surface tension, reducing the surface tension or introduction of surfactants, in fact, in fact, increase the stability. So, next question is. So this is the next question. It says, consider the problem of Marangoni convection in the box, open only at the top. If the left wall is hot and the right wall is cold, the bottom wall is adiabatic. Which of the below convection pattern is likely to occur due to thermal Marangoni effects if the surface tension decreases linearly with temperature? So here we can say that the surface tension is gamma. So if I write gamma naught is less, gamma naught is high again. So if we analyze this picture, if the surface tension is less and here on the right the surface tension is more, then generally the flow is from lower surface tension to higher surface tension. If we look at the four configurations, only the first one agrees to such a flow, and therefore only the flow configuration A is possible. Therefore, the correct option is option A. So all the other flow configuration we see a net leftward movement. In this case, entire leftward. In this case, leftward. Therefore, these are not possible. So, so that is a that is the only configuration which is correct. Yes, is there any doubt? You can ask. I'll copy the next question. So, there is no question. I'll continue. In the discussion of the Bernard-Marangoni convection in the course, we had ignored the role of buoyancy forces. What is this? When is this assumption justified? So, in one of the assumptions was that the role of buoyancy is neglected in setting up the Bernard-Marangoni convection. So, let's look at the options. The options is when Reynolds number is small, when the Marangoni number is large, when the Grashof number is large, when the Rayleigh number is very small. So, so let me write the business equations. So, so the business equation go like, um, so A is like Prandtl number into d by dt of d by dt into del square of theta cap, which is negative of omega cap. And the second equation is d by dt minus of del square omega cap, which is equals to minus Rayleigh times uh, del square theta reverse cap. So one of the assumptions that we do in equation number B is that B in equation B we have d by dt minus del square omega cap is equals to minus Rayleigh del square theta reverse cap. So if we look at this term, when the Rayleigh number is really small, that is, so the Rayleigh number is very, very less than 1, then the RHS can be assumed to be 0. And we know that Rayleigh number is equals to the Grashof number and the Prandtl number. So, and more importantly, the Grashof number inherently has the information regarding buoyancy and viscous forces. It is basically the balance of buoyancy, viscous, and inertial forces. So, info regarding regarding buoyancy and viscous forces. So basically, the Grashof number has to be small. Therefore, for the assumption to hold, the Grashof number is should be small. So the Grashof number is supposed to be small. So the correct option is Rayleigh number is small. So option D is the correct option. Rest of the option Reynolds, Marangoni number, Grashof number, these are all these conditions are wrong. So, so the correct option is where the Rayleigh number is small. Let's look at the next question. Consider a fluid with viscosity mu and the density rho with a flat consider a fluid with viscosity mu and the density rho with a flat free surface at y equal to 0. The fluid is contained in the region y is less than 0. The gas is above is assumed to be passive. The interface is always assumed to be flat and subjected to a linear temperature gradient T of x. So T of x. This in turn generates a surface tension gradient due to its dependence on temperature via the equation gamma is equals to gamma naught 1 minus beta T minus T naught. What is the correct expression for the velocity gradient at y equal to 0 as obtained from the tangential stress balance? So firstly, let's write down what is given. So given we have rho, we have mu, and then the surface tension varies as gamma is equals to gamma naught 1 minus 1 minus beta times T minus T naught. And if we draw the diagram, it is 0, comma 0, and so the fluid is only in the negative region of y naught. Oh, sorry, negative region of y. So the fluid is below. So y is equals to 0. So here as fluid. So the fluid is passive here. So T of x is linear. So it is asked find del u by del y at y equal to 0. And we also know that del gamma by del x is equals to minus beta gamma. So yes, if we differentiate t with respect to x and t of x is linear, then we straight away we will get the del gamma by del x as minus beta gamma naught, and del gamma by del gamma by del y is equals to 0, as temperature is only a function of x. So now we'll set up the problem. So another important detail is that the normal is can be written as 0 comma 1, as it's in the positive y direction, and the tangent t cap can be written as 1 comma 0, which is in the x direction. So the tangential stress balance can be written as n hat dot tau dot t hat. So this is the tangential stress balance. Therefore, in the plus side, minus n hat dot tau dot t hat minus is equals to minus t hat dot del s gamma. So the right hand side. So let's first take the RHS, and the RHS can be written as minus 1 0 dotted with del S gamma. So del S gamma, del S. So del S gamma can be written as del gamma by del X I cap plus del gamma by del Y J cap. So del S gamma is equals to minus beta gamma naught. So we just saw that because temperature is linear, so del gamma by del x will have a value of minus beta by gamma naught, and the del gamma by del y will be 0. And taking the dot product will give us minus 1 into minus beta gamma naught, which is equals to beta gamma naught. And if we look at the LHS, straight away the first term will go and hat tau double dot t hat. So for the positive, because the fluid is passive, the first term will be 0 and then minus tau. And this is just Newton's law of viscosity. We'll get tau, which is equals to simply minus mu del u by del y. And this is at y equal to 0. We want it at y equal to 0, therefore we'll substitute y equal to 0. This implies that del u by del y at y equal to 0 is equals to minus beta gamma naught by mu. So therefore, this is the correct answer. And this is option A. No, option B. Option B. So, so that is the answer. I think you understood. So I'll be skipping the fifth question. I'll take this up in the next class. So we'll move to the sixth question, skipping the fifth question. So sixth question says, So the question reads, in the course, we have seen the stability chart in Marangoni alpha plane as shown in the image below for different values of Nusselt number. Why does the region of stability increase with the increasing Nusselt number? Marangoni number increases with increasing Nusselt number, hence higher Nusselt pushes the stability boundary upward. Marangoni number decreases the increasing Nusselt number, hence higher Nusselt number pushes the stability boundary upwards. Heat is more effectively transferred to the surrounding medium at higher Nusselt number, hence more stabilization. Heat is stored more effectively inside the medium at higher Nusselt number, hence more stabilization. So, so we can say that given stability region increases as Nusselt number increases, and the reason is Nusselt number is equals to convective heat transfer rate by conductive heat transfer rate. Therefore, as Nusselt number increases, heat transfer to surrounding medium also increases, having a stabilizing effect. So, therefore, the correct option is option C. So consider a thin liquid layer heated from the bottom and the interface is exposed to a passive gas. The liquid layer is found to exhibit Bernard-Marangoni convection. What causes this instability? So warmer fluid being lighter rises up from the bottom and cooler fluid near the interface sinks, causing the instability. Tiny fluctuation in temperature at the interface cause surface tension fluctuation, causing the instability. Excessive heat causes evaporation, causing vapor to form at the interface, leading to onset of the stability. Tiny fluctuations in temperature in the bulk generate fluctuation in density and buoyancy, causing the instability. So, going through the course, it is clear that the correct option is option B, that the tiny fluctuations in temperature at the interface cause the surface tension fluctuation and therefore driving a Marangoni flow, which causes this instability. So, option B is correct. And the next question is, the next question says, which of the three statements below is related to Nusselt number? So the Nusselt number is the ratio of convective heat transfers to convective heat transfer to conductive heat transfer. Correct. It is a ratio of heat flux to diffusive heat flux. So convective heat flux is convection and diffusion is basically very similar to the conduction of heat. So therefore, it is also correct. And the third is it is just temperature gradient in the non-dimensional flow. So if you have gone through the course, this is also the correct option where theta cap. So it is defined as theta cap is equals to T minus T naught by T1 minus T. So the non-dimensional uh, form of temperature gradient is also the Nusselt number. and is related to thermal runaway. So the correct option is option D. So I'll quickly take a break and then we'll resume the next week lecture. So so we'll look at the week 11 assignment. I'll quickly take a break and go over the solutions and then we can discuss it. Okay, so we'll resume the session. Next, we'll look at week 11. So let me get the first question. So in week 11, we go over the Kelvin-Helmholtz instability, and then we look at the stability of the perturbation that is generated on the interface between the two fluids. The fluids are considered to be inviscid, and then we see different configurations and their effect on the stability. So let's look at the first question. Consider a 2D version of Kelvin-Helmholtz instability described in the XZ plane with the flow being in the x direction. So XZ plane. It's XZ plane. And then the flow is in the x direction. The pressure jump condition involves a curvature term, which is given. Let me read out the question. The curvature term del dot n at z is equals to eta x comma t, where eta is the interface. The linear limit. In the linear limit, the curvature simplifies to eta xx. What would be the first nonlinear correction to the curvature beyond the linear limit? So it is given that del dot n is the curvature, and the curvature at z is equals to eta x comma t. So we know from our earlier lectures that del dot n is simply minus h. So in this case it's eta. So eta x x by 1 plus eta x whole square whole to the power 3 by 2. And so we have essentially we have eta x, and if we write this down, we arrange eta x x into 1 plus eta x whole square whole to the power minus 3 by 2. So we know the binomial expression when n is not an positive integer. So 1 plus x to the power n is equals to 1 plus nx plus n into n minus 1 by 2 factorial x square plus so on. So if we expand the term del dot n at z is equals to eta x comma t, we get eta xx 1 plus 3. So it is 3 by 2 eta square x and therefore the plus. So the higher order terms are later. So the first order is just minus eta xx. Then the second order will be order. Okay. The leading order is just eta xx. So the first order will be eta xx 3 by 2 eta x whole square. So therefore the correct option is option C. So the option C is 3 by 2 eta xx eta x whole square. So this is the correct option. So this is simply from the coming from the binomial distribution. Let's go to the next question. So the next question is So the next question says, in the analysis of Kelvin-Helmholtz instability, we assume that the flow in each fluid is governed by the Laplace equation. What conditions are used to justify such an analysis? So we have given del square phi is equals to 0, where, where u vector is the gradient of phi. So this is the condition, and this can be because this is primarily because del cross gradient of phi is always equals to 0, and this implies that del cross u is equals to 0. So therefore the flow is irrotational, and del dot u is equals to del dot gradient of phi, which is equals to del square phi. So therefore, both the compressibility and irrotational are needed. So the correct answer is option D. So let's look at the next question. Consider a flow configuration shown in the figure below. The following question contains special cases for different combinations of densities and velocities in the fluid. If u1 is 0 and u2 is not equal to 0, rho1, rho2 is equal, and the surface tension is 0, which of the below statements is true? The flow is stable to perturbations of all wavelength. The flow is unstable to perturbation of all wavelength. The stability of the flow depends on the magnitude of velocity. The flow is stable to perturbations with large wavelengths. So, here given, we'll write down what is given. So u1 is 0, u2 is not equal to 0, rho1 is equals to rho2 is equals to rho naught, and gamma is 0. So this implies no gravity effects. So we know that the equation for stability is given by s square plus as plus v equal to 0, where if we see s is given as s square plus s into 2ik rho1 u1 plus rho2 u2 by rho1 plus rho2. Plus it is minus k square 1 u1 plus rho 2 u2 by rho 1 plus rho 2. So minus mg rho 2 minus rho 1 by rho 1 plus rho 2 plus m cube gamma by rho 1 plus rho 2. So we have out of all of these terms, some of these terms get cancelled right away. So the gravity term is 0, the surface tension term is 0. And then if we see the stability, that is if we write a square minus 4b, this implies we'll get s real part is equals to k square by u1 minus u2 whole square. So as S is always positive, SR is equals to a positive number. Therefore, SR is real. So this implies that the flow will always be unstable. So it's simply put, if we write down this equation and then we remove the gravity term, the gravity gets cancelled because rho 1, rho 2 are same, and then the gamma is equal to 0. And if we write down a square minus 4b, which is just the condition for the discriminant, then we'll get SR, and SR will always be positive. Therefore, so the square root under SR will always be positive, which implies that SR is real. Therefore, it will always be unstable. So the flow is unstable. Okay. So
Transparent wool is the no texture of almost every.
So the let's see the fourth question. The fourth question says, let the configuration given in problem 3 represent air-water interface. Assume the velocity of water U2 be 0. If the speed of the air continuously increase from 0, what is the approximate wavelength that will first become unstable according to linear theory? So okay. So let's write down what is given. Given is rho 1 is less than rho 2, that is air density is less than the water's density, and u2 is 0, and u1 starts from 0. So the air above is just starting to blow, and we want to know that when is the um, so the question is, if the speed of air continuously increases, what is the approximate wavelength that will first become unstable according to linear theory? So we have S, which we have written above. Uh, so let me write down S again. So S, if we work it out, it comes out to be IK by rho 1 plus rho 2 plus minus k square rho 1 rho 2 by rho 1 plus rho 2 whole square u1 minus u2 whole square minus mg rho 1 minus rho 2 by rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2 whole power 1 by 2. So this term is greater than 0. When it is greater than 0, then we have the first. So when it is greater than 0, then we have the unstable form. So then therefore lambda is equals to 2 pi by m, which is equals to 2 pi by the root gamma rho 2 minus rho 1 g, which is equals to 2 into pi into 2.7 into 10 power 2.7 into 10 power minus 3. So this comes out to be 16.6 mm. So the correct option is option A, 16.6 mm. So fairly. So you have the next question to be. So the next question is, consider the configuration given in problem number 3. If U1 is equals to U2 is equals to 0 and rho 1 is greater than rho 2, that is the top fluid is denser and surface tension is not equal to 0, which of the below statements is true? So given rho 1 is greater than rho 2 and U1 is equals to U2 is equals to 0. So basically rho 1, rho 2. So the top fluid is much denser. So we'll have S is equals to rho 1 minus rho 2. This can be derived from the earlier expressions. G minus MQ gamma by rho 1 plus. So the flow, for the flow to be unstable, the term in the square root should be greater than 0. So if we make it rho 1 minus rho 2 by 1 plus rho 2 mg minus mq gamma by rho 1 plus rho 2 greater than 0. So firstly we get rid of the denominator and then this comes out to be m should be less than rho 1 minus rho 2 by gamma to g, and we take the square root. So lambda is equals to 2 pi by m, which is equals to 2 pi gamma by rho 1 minus rho 2 g. So the correct option is that the flow is unstable to perturbation of all small wavelength and is stable for wave numbers beyond a critical value. So, so for m which is less than this value. So for values of m which is less than this value, uh, so for m which is less than this values, it is unstable, and for greater than this particular value, it is stable. So that's the correct option is option D. So the next question. So so the question, let's look at question number 6. So the question 6 is, consider the configuration given in problem. So consider the configuration. Okay, again we have the same question. Consider the configuration given in problem 3. If U1 is not equal to 0, u2 is not equal to 0, g is equal to 0, and surface tension is not equal to 0, which of the below statements is true? So it is given u1 is not equal to u2 is not equal to 0. G is equals to 0. This implies rho1, rho2, and gamma is not equal to 0. So, so again we'll write down S, which is equals to minus ik by rho1 plus rho2, and then plus minus k square rho1 rho2 by rho1 plus rho2, and then you have u1 minus u2 whole square minus mg. So this term drops out, the gravity term drops out, and then we are left only with m cube gamma by rho1 plus rho2 whole power 1 by 2. So this will simply give us the plot of SR and wave number k, and it will look like this, where this is k cut off. So this is the region is stable and this is unstable. So whenever k is small, we have long waves, and when k is high, we have short waves. So for different configurations, we see the stability and instability. So I'll quickly take a break here and come back. Take this. Yeah. Um, I'll, okay, so we looked at the sixth question. The correct option. Okay, I didn't mark the correct option. So the critical wave number of stability depends on the difference in velocities. So it does depend on velocities. So this is the difference in velocities. And the second option says all long waves are unstable independent of the value of surface tension. So all the long waves here in this region are unstable, and the short waves are stable for a wavelength below critical value. So regions here. So for a wavelength below this threshold, there is a so not here, so it's above here. Above a cutoff value, we have stable regions. So the correct option is option D. So let's look at the next question. So again, let's look at the next question. The next question says, consider the configuration given in problem 3. If u1 is equal to 0, is not equal to 0, and u2 is equal to 0, and then the rho 1 is less than rho 2, that is the bottom fluid is heavier, and the surface tension is also not true, then the question says, which of the statements is true? The flow is always unstable to perturbation of all wavelength. The flow is unstable only if the my laptop is about to die. You have to connect the charger. So the flow is the flow is always unstable. The flow is unstable if the velocity u1 crosses a certain critical value, and the flow is always stable to perturbation of all wavelengths. So we'll write down S again for this question, and let's copy the S. Yeah, so S. Okay, I'll rewrite the S term here again. So S is equals to minus IK by rho 1 plus rho 2, and then plus minus IK. So minus K square rho 1 plus rho 1 rho 2 rho 1 plus rho 2 into u1 minus u2 whole square minus mg rho 1 minus rho 2 by rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2. And all of this is under a square root. So if you take the term under the square root, we have we have we have k square rho 1 rho 2 u1 square by rho 1 plus rho 2 minus m cube gamma by rho 1 plus rho 2. So this is under the square root, and So when u1 is increasing, all the terms inside the square root are positive, and therefore SR is real and finite. Therefore, the flow is unstable for all wavelengths. So the correct option is option B, that the flow is unstable only if the velocity u1 crosses a certain critical value. So there's a negative sign here. And once it crosses the threshold of this term, that is m cube gamma rho 1 plus rho 2, once the value gets more than it, then the term becomes positive, and therefore we have an unstable configuration. So that is the correct option. And the last and final question is, so the question says, which assumptions were used for the linear stability analysis of Kelvin-Helmholtz instability discussed in the course? The two fluid streams are assumed to be inviscid. The two fluid streams are assumed to be irrotational. The amplitude of disturbance at the interface is assumed to be small. The velocity perturbations are assumed to be small. So the first two reasons are correct straight away, that the fluid streams are inviscid and irrotational. We have seen it earlier in the question where del square psi is equals to 0, where we define velocity u to be gradient of phi. So first two are correct. The amplitude of disturbance is also small. Only then we are able to incorporate the linear stability analysis. The eta should be small. So third is also correct. And the velocity perturbations are also assumed to be small. So the nonlinear terms u square also drop out. Only then we can have a linear stability analysis. Therefore, option A is correct. So with that, we come to the end of week 11 assignments as well. So I'll see you in the next class, Friday class. So that will be the final doubt session, and we will go over assignment 12 on Friday, that is 10th October. So that's all. I'll stop here. Thank you.